inconvenience, but it's a pleasure to hear Jorge Vitório, who will be speaking on singular foliation with trivial canonical classes. Please.
Thank you, Jacob. Well, due to the special circumstance, everybody is allowed to sleep. I will not be sad. So I will.
Except you.
Well, who knows? I want to talk about this work it's a joint work with Frank Lohay and Frédéric Touzé from the University of Rennes. And it deals with it deals with foliations, algebraic foliations on projective manifolds, on complex projective manifolds, which I will define in a minute. Let me start recalling what is a smooth foliation. It's just defined by a subbundle of the tangent bundle of X, which is closed under the Lie bracket, right? So in characteristic 0, in the analytic category, this implies that locally your foliation is the relative tangent bundle of a vibration. Of course, locally here means in the small ball in the Euclidean topology. TF is the tangent bundle of the foliation, and NF is the normal bundle of the foliation. So this talk fits in this general philosophy that TF and NF, the tangent and the normal, should govern the geometry, dynamics, and properties, general properties of the foliation. Smooth foliations in the complex setup are very rare. While singular foliations abound. It's fairly easy to construct singular foliations. But what is a singular foliation? Well, instead of looking to subbundles, we just look to coherent subsheaves, which are closed, still closed under the Lie bracket, and we ask that the singular set is somehow minimal. We suppose that the sheaf is saturated inside the tangent bundle. In other words, we ask the cokernel of Tx of the inclusion to be torsion-free. Okay? The loci where the Tx over Tf is not locally free is the singular locus of the foliation, the singular set of F, and it has codimension at least 2 due to our condition here. Okay? So the dimension of the foliation is just the generic rank and the codimension of Tf, and the codimension is the generic rank of the cokernel. Well, let me start with some examples. Every projective manifold carries a unique foliation of codimension 0. It's the projective manifold itself. You can see it as a foliation. It also carries a unique foliation of dimension 0. Again, the projective manifold itself. The only thing is that here the tangent sheaf of the foliation is just the tangent sheaf of the manifold, and here the tangent sheaf is just 0. So this sounds kind of silly, but somehow says that, well, the theory of foliation should be thought as a kind of generalization of the theory of varieties, of manifolds. And there is a general process that given a foliation on a projective manifold Y, in a rational map from another manifold X to Y, we can always pull back them. So this makes this definition, at least this definition of foliation of dimension 0, less silly, because you see that from this, fibrations appears as pullbacks of foliation by points on the base. When this map is dominant, codimension is preserved. And there is another example, is a closed rational one form defines a codimension 1 foliation. The kernel of it will define a codimension 1 foliation. If dimension X is equal to, then any rational one form defines a foliation on X. The integrability condition is empty here. And finally, if I have a representation of the fundamental group to the automorphisms of P1, then I can define a P1 bundle together with a flat connection, and the flat sections will form a foliation. Right? There is also a version of this, a logarithmic version of this construction. I don't want to enter in details. And variations, we can put all these constructions together. And the point is that so far, all known examples of codimension 1 foliations can be constructed by combining the examples above. Nothing besides these exist, are known so far. No examples are known. And essentially here we have a very rich source of examples, right? The other are highly structured, but here the things tend to be very, very, very rich. Okay? So what the problem that we are interested in is the following. We want to look at the canonical bundle, which is just this line bundle of the foliation, which away from the singular set is just the bundle of differential forms of top degree along the leaves. And our goal is to describe the structure of codimension 1 foliations when Kf is numerically trivial, meaning that its rational Chern class is 0. Okay? So that's our problem. That's what I want to tackle. And let me recall some previous results. Well, in codimension 0, there is Bogomolov's theorem, some prefer to call Boville-Bogomolov, which says that after a finite italic covering, a projective manifold, smooth projective variety, a complex smooth projective variety with 0 Chern class is a product of an abelian variety with a Calabi-Yau manifold, which is just a simply connected variety with 0 Chern class. In codimension 1, on a compact Keller manifold, there is a result of Frédéric Touzé from 2009, which proved that after finite italic covering, at least one of the following assertions holds. Well, X is a product of a Calabi-Yau and a torus, and F is the pullback of a linear foliation on the torus. X is a P1 bundle over a manifold with 0 Chern class, and F is everywhere transverse to the fibers. Or F is an isotrivial, the analytic type does not change, fibration by hypersurface with 0 Chern class. There is also results, when X has dimension 3 and is projective, this was first proved by Druel. Indeed, I think it was part of his PhD thesis. I'm not really sure about that, but from 99. On the case of P3, this has been also classified. Of course not, but they didn't use this language, but it was due to Cerveau and Isneto in 96, and showed that they fit in 6 families. Foliations on P2 that you pull back, foliations of degree 2, let's say. Pencil of cubics with a triple hyperplane as a member, pencil of quadrics, logarithmic 1 forms with poles on 4 hyperplanes, logarithmic 1 forms with poles on 2 hyperplanes and 1 quadric. These are the defining elements of the foliation. And finally, an action of the affine group on the 3 copies or on the third symmetric power of P1, the natural action. You just make the affine group act on C and look on the induced action. Unaware of this result, Polishuk in 97 classified these same foliations under this hypothesis under the additional assumption that singularity of F has a smooth curve as one of its connected components, and he ended up with only these 2 examples. But it was already done by Cerveau and Isneto. And the thing that there are these 2, there are further motivations. No? More recently, there is a paper by Peternel where he establishes that the existence of foliations with numerically trivial canonical bundle, not necessarily of codimension 1, is the only obstruction that a non-uniruled manifold carries to have a generically ample cotangent bundle. And also, these foliations come naturally from holomorphic Poisson structures. These were indeed the original motivation of Polishuk and Druel. The things were phrased in 2 different languages, and somehow that's why we have this duplicity of results with one school knowing nothing about the other. Okay, so let me state the main result that I would like to explain here. So let F be a codimension 1 foliation with trivial canonical class. Then it is at least one of the following holds. F is uniruled, meaning that through a general point there is a rational curve tangent to F, or F admits a rational first integral, meaning that the general leaf of F is algebraic, or F is defined by a closed rational one form with coefficients in a torsion line bundle and without divisorial components in its zero set, which says essentially that our foliation, if it's not by algebraic leaves or comes from smaller dimension, it is very highly structured. It's essentially given by a closed rational one form. After a finite italic covering, it will be given by a closed rational one form. Okay, that's the definition of uniruled that I told you. And what I want to discuss in this talk, I would give a brief idea of the techniques on how we achieved the proof of this result. Essentially, if you want, we have 3 steps. We have the first step, which is arithmetic. The second, which is analysis. And the third, which is algebraic geometry. Of course, we use these 3 techniques in very elementary way, but using deep results of others, right? The use is elementary of deep result of others. An elementary use. Okay, so let me start with the starting point. Part of the philosophy is the following. When this canonical bundle is negative, you expect your foliation to have algebraic leaves, or at least to be foliated by a subfoliation with algebraic leaves. Because this is Miyaoka's result. It's one of foundational results for the Mori theory of foliations, for the inexistence so far rational theory of foliations. Perhaps this is the founding result. So it says one possible formulation is the following. So if F is a foliation on a polarized projective manifold, just a projective manifold with an ample line bundle or ample divisor, if the canonical bundle of the foliation intersects this canonical this divisor negatively, or the nth minus 1 part of it, then F is uniruled. More precisely, moreover, if TF is age semi-stable, in the sense of the talk of yesterday or earlier today, then the generic leaf of F is algebraic and rationally connected. So you look to the Hadamard-Zillman filtration, and the first piece will have negative intersection with age, and this will define this foliation by algebraic leaves inside F, which can be the whole F, and will give the rationally connected connectedness of the leaves. Okay? So, in particular, that's the point. If we start with a foliation which has trivial canonical bundle, so it will intersect it as the intersection will be 0. So the maximal destabilizing sheaf defines a rationally connected foliation, and we can conclude that the foliation is uniruled. So if we just discard the first possibility of the theorem, we can assume that our tangent sheaf is age semi-stable. Okay? So we start from that. We have a TF semi-stable and KF equals 0. So that's said in another way there. And the first idea, that's where the arithmetic enters, is that to prove that something is given by a closed rational one form, we know since Sophus-Lee that the only thing that we have to do is to produce an infinitesimal symmetry, a transverse infinitesimal symmetry, which means that we have to produce a rational vector field whose local flows preserves the foliation. In characteristic 0, this is extremely hard. We don't know how to bound the polar set of the vector field. It's very complicated. But it can be very easily phrased algebraically, so it means it has a meaning in every characteristic. And in characteristic P, it's on the contrary. It's very easy to do. Because if you have a vector field in a positive characteristic, you can do an operation that we can't do in characteristic 0, which is take p powers. So if you take a p power of vector field, this is still a vector field. And we can have, if you take a vector field with tangent to the foliation, then the p power will be automatically infinitesimal symmetry. Somehow it's intuitive and the computation is not very hard. And it somehow would give, this seems to give a way to produce the sought infinitesimal symmetry. Of course, if this infinitesimal symmetry is not transverse, we can't prove that the foliation is given by a closed rational one form. But then there are the results by, I don't really know who I think it's Aplicada, who proved that when these things are p-closed, then indeed we have rational first integrals in characteristic p. So either one of these VPs is not tangent, and we have our sought rational, our sought integrating factor, we can prove that is given by rational one form, or the things are p-closed. But this only works in characteristic P and has one major problem. It works for every foliation. If you have an argument that works for every foliation, it has to be trivial, right? So, but the thing is the following: is if our foliation is semi-stable and has trivial canonical bundle, we can control everything. We can bound the degree of the divisors that appears. We can doing these results by even in the length of strongly semi-stability. We can control the results by the results like Scheffer-Baron, the Langer. We can control everything, and we can bound a priori the degree of the vector fields involved and prove something like this. So let X be an n-dimensional polarized projective manifold, F semi-stable foliation of codimension 1. If Kf intersects 0, the n minus 1, then at least one of the following is true. Well, I'm supposing that the foliation and everything here is always are defined in a finitely generated Z algebra. Then we can prove that for almost every maximal prime P contained in R, the defining ring of everything, the reduction modulo P is P-closed, or F is induced by a closed rational form with coefficients in a flatline bundle and without divisorial components, but this second in characteristic 0. Since we bounded everything, we are able to lift. That's fantastic. But to deal with case A, there is a conjecture. It's conjectural. We don't know if that's true. We would like to say that in this case, the foliation has a rational first integral. This is a conjecture of Aplicada, Scheffer-Baron, and Taylor, which predicts that. And this conjecture is a generalization of a conjecture by Grothendieck and Katz, which is wide open. And it seems that we are in bad shape. But not everything is missed because we know something about that conjecture. We know that it somehow imposes restrictions on the singular set of the foliation. So using basic index theory of foliations, under further assumptions on our variety, this is Baumbach index theorem, if you want, and using the local structure of singularities of P-closed foliations, described by McQuillan, we have that in that case, we can refine that result under this assumption and show that either the foliation is uniruled, which comes from the existence of non-canonical singularities, or the foliation is rationally connected, and we are done, at least under this assumption, which is somehow artificial. It's there just to be able to use this index theory. So we had an almost proof, at least a conditional proof, very quick and not very complicated, but which falls short from proving the general case. So somehow we have now to control, to have more information about the variety X. of the manifold X. But already with only this partial result, there is a class of varieties where these things hold true. It's a kind of Fano manifolds with peak Z, for instance. And we could give a generalization of this result by Cerveau and Lins-Neto and obtain a complete classification, quite detailed in the situation, which is summarized in this table. This is Cerveau-Lins-Neto theorem. And then there are only a few classes of Fano-free folds, and we can give a very, very precise description of the foliations with trivial canonical bundle there. And the nice thing is that also implies the classification of these free folds carrying holomorphic Poisson structures. To do that, we have still to prove something extra. It's a generalization of a classical result by Halfen about the number of multiple fibers in a pencil that I could not find in the literature. But something that this seems to be a result that very popular in foliation theory, but I never saw any modern paper in algebraic geometry mentioned in it, which says that if you have a map from Pn to P1, we have, with generic fiber irreducible, we have at most 2 multiple fibers. We could generalize it for other varieties, okay, following approved by Lins-Neto. Anyway, so we have 2 now. So this is the arithmetic part of the talk. So this reduction modulo P. I feel that I can talk about arithmetic without understanding. So let me talk about analysis, but without understanding also. So, and this is enters to prove this unirootedness criterion. Well, there is a very old result by Rosenlich, well, very old, from the 60s, that says that, or perhaps earlier, well, there's this result by Rosenlich that says that a projective manifold that carries a holomorphic vector field vanishing at some point is uniruled. And this has been, there are conjectural generalizations of this result, many of them. One of it is appeared in a preprint by Paternel last year, that the existence of a holomorphic section of stereo power of Tx with coefficients in a flatline bundle vanishing at some point would also imply the unirooting of X. And we were able to verify this conjecture. In particular, we proved that if F is a foliation on a non-uniruled manifold with trivial canonical bundle, or trivial canonical class, then F is smooth and fits into 2Z result. So this also deals with this non-uniruled manifold, non-uniruled realm class of manifolds, and we have more information even without imposing condition on the codimension of F. And the ingredients, that's where I think that we are using analysis, because we have to use the Mail's integrability theorem or integrability criterion, basic Rod theory, and books on the Mail Paul-Paternel criterion of uniruledness, which allow us to produce a metric, a singular metric with positive curvature on the canonical, and we start from there by mimicking some ingredients of the proof of Bogomolov's theorem that I mentioned in the beginning. So that's the analysis part of the talk, very brief, as my knowledge on it. And the third ingredient comes from algebraic geometry, again, by rational geometry perhaps, and it comes from the deformation theory of curves, or in particular of rational curves. So if X is uniruled, this means that there are this object. That's, if you want, you can take this as a definition. You have a morphin from P1 to X such that the pullback of Tx is generated by global sections. These are the free morphins. The good thing about these guys is that the deformation theory of them is pretty straightforward. So the space of morphisms is smooth at this point, and its tangent space at F is naturally isomorphic to this cohomology group. And what happens is that when you have a foliation on X, we can try to do the following. We can try to take a morphism from P1 and try to deform it in such a way that points moves on the same leaf. So somehow we are doing a deformation of everything together. And this will indeed define a foliation on the space of morphisms. So it's the study of this foliation which will allow us to deal with this class of manifolds. What happens is that we can control very, very well this foliation defined on the space of morphisms. We can in particular control the dimension of the Zariski closure of the generic leaf. And it will be something between the dimension of f tang and the dimension of f tang plus 3. When it's 0, this, well, let's say plus delta here. Let's call it 3, so dimension of the Zariski closure of the generic leaf will be the dimension of L plus delta. So there the 0 is meaning delta equals 0. Then this means that the leaves of f tang are algebraic. When the leaves have dimension 1, we can prove that this foliation is very particular. It will be transversely Euclidean. 2 will be transversely affine, and 3 will be transversely projective. This somehow is related to the kind of transversal dynamics of the foliation. There is essentially no dynamics. The leaves are algebraic. Here says that the dynamics is modeled after translations, modeled after affine transformations, and modeled after projective transformations. So somehow we have these assumptions on the tangent direction which allows us to control the transversal dynamics. And either F admits a subfoliation, the conclusion is that either F admits a subfoliation by algebraic leaves or F is transversally projective. So studying the tangential foliation, we can prove that for any F on a uniroled variety. Of course, if I take a general F with KF very positive, we will always end up with this situation. The foliation will be a foliation by points, not very interesting. But in this situation here, F codimension 1 and in dimensional uniroled projective manifold, if I have a generic free morphism and I call delta 0 this H0 and delta minus 1 this other H0, then we have the following assertions. F is transversely projective, or the foliation is the pullback by a rational map of a foliation G on the projective manifold of dimension n minus delta 0 plus delta minus 1. And if delta minus 1 is positive, then F is uniruled. And we can add something to it. If X is rationally connected and F is an embedding with ample normal bundle, so this curve is not just a map, it's a map which is an embedding, and the image has ample normal bundle, then we can replace transversally projective by transversally affine in item A. So there is a study of the variation of the transversally projective studies, the structure, Harshon extension of formal rational functions, and adaptation of Mori bend and break argument to deal with this last part. So this also gives pretty good, comes very close to the theorem, but do not prove the theorem. Since we have we can always, if X, in the case X is rationally connected, we can always obtain this, take a generic, an embedding with ample normal bundle of P1, and we can achieve transversally affine, but we want more. We want given by a closed rational one form, which means transversally Euclidean. But also in the uniruled case, it doesn't get closed. It stops in transversally projective, so we need something more. So we have now to mix these three ingredients. And I will not enter in details. So let's just give an impressionist or expressionist idea how it goes. We use positive characteristic argument to impose constraints on the singular set. Deformation of rational curves implies the foliation is transversally projective. Existence, so this gives the existence of invariant divisor with good combinatorial properties, and logarithmic versions of the arguments that I have not explained to prove the uniruled criterion allow us to prove that F is smooth. Oh, that's it. And we get the theorem. And we can now go home now. Okay, thank you.